Light changes color as it travels across space. Every single photon gets stretched during its billion-year journey to Earth. You assume starlight arrives exactly as it left distant stars. That assumption is wrong. Tonight we're discovering how this color changing became our most powerful cosmic measuring stick. We'll trace why every galaxy appears to flee from us at impossible speeds. Before we dive into this light detective story, drop a comment about where you're listening from. If you enjoy these cosmic mysteries, consider subscribing. These late-night journeys through space and time are meant to be shared. Early 1900s astronomers faced an impossible discovery. They pointed their instruments at distant galaxies. Every single one showed the same bizarre pattern. Light that should appear blue-green glowed red instead. This wasn't one galaxy. This was every galaxy they could observe beyond our immediate neighborhood. Scientists use something called spectroscopy. Think of it as reading light's fingerprint. Every element creates specific colors when it glows. Hydrogen makes particular lines. Calcium creates others. Iron has its own signature. But in distant galactic light, all these fingerprints had shifted. Every hydrogen line moved toward the red end of the spectrum. Every calcium feature drifted from its expected position. The pattern was universal and undeniable. Edwin Hubble confirmed what seemed impossible. Galaxy after galaxy revealed this systematic color stretching. The more distant the galaxy, the more its light had been transformed during its cosmic voyage. Something fundamental was happening to light itself as it crossed the universe. Hubble discovered the universe's strangest relationship. The farther away a galaxy sits, the faster it races away from us. This follows a perfect mathematical pattern that governs everything we can see. Picture galaxies at different distances. Those 100 million light-years away recede at specific speeds. Double that distance to 200 million light-years. The recession speed doubles as well. This isn't galaxies randomly flying through space. This is space itself expanding uniformly. It carries every galaxy along like raisins in rising bread dough. Hubble's law shattered our assumptions about cosmic architecture. The universe isn't static and unchanging. It's been expanding since its birth. Every region of space grows larger over cosmic time. The redshift we observe in galactic light provides direct evidence for this fundamental expansion. Light behaves like a wave as it travels through space. Think of waves on water or sound waves in air. When space itself stretches, it stretches the light waves traveling through it. This stretching makes light waves longer. Longer waves appear redder to our eyes. That's why scientists call this phenomenon redshift. Blue light has short wavelengths. Red light has longer wavelengths. When space expands during light's journey, it pulls those wavelengths apart. Blue becomes green, green becomes red, red becomes infrared. The amount of stretching reveals how much space expanded during the light's travel time. More stretching means the light traveled longer through expanding space. This color change acts as a cosmic timestamp embedded in every photon that reaches Earth. Edwin Hubble made the most shocking discovery in astronomy history. He measured the distances to nearby galaxies using special stars called Cepheid variables. These stars pulse with clockwork regularity. Then he measured how fast these same galaxies were moving away from us. He used the redshift in their light as a cosmic speedometer. What he found defied all expectations. Every single galaxy beyond our local group was racing away from the Milky Way. Not just moving randomly, fleeing systematically. The pattern was perfect and terrifying. Closer galaxies moved away slowly. More distant galaxies fled faster. The relationship was mathematically precise. This discovery demolished the concept of a static universe that had dominated human thinking for millennia. Scientists initially thought galaxies were flying through empty space. That explanation seemed logical but turned out to be completely wrong. The real answer is far stranger. Space itself expands like a balloon being inflated. Galaxies remain essentially stationary within their local space, but the cosmic stage stretches beneath them. Think of drawing dots on a balloon. As you inflate it, the dots move apart, but they're not flying across the balloon's surface. The surface itself grows larger. This explains why redshift increases with distance. Light traveling through more expanding space gets stretched more. Light from nearby sources barely stretches at all. The fabric of space-time has been growing for nearly 14 billion years. The redshift we observe is our direct evidence for this mind-bending reality. Light takes time to travel across cosmic distances. This creates an extraordinary side effect. Looking into space means looking backward in time. Light from the sun takes 8 minutes to reach Earth. When you see sunlight, you're seeing the sun as it was 8 minutes ago. Light from the nearest star takes 4 years. You see it as it was 4 years in the past. Distant galaxies reveal themselves as they were millions or billions of years ago. The most distant objects show us the universe when it was young and dramatically different. Redshift tells us exactly how far back in time we're looking. Larger redshift means older light. Higher redshift reveals earlier cosmic epochs. Every photon carries a timestamp from its moment of departure. The universe's expansion history is written in the colors of distant starlight. Before redshift, measuring cosmic distances was nearly impossible. Astronomers could only estimate distances to the very nearest stars and galaxies. The rest of the universe remained unmeasurable. Redshift changed everything. It provided a direct relationship between color shift and distance. Measure a galaxy's redshift, and you know how far away it sits. This works because expansion rate is constant throughout the observable universe. Hubble's constant, about 70 kilometers per second per megaparsec, gives us the cosmic conversion factor. Scientists can now map the three-dimensional structure of the universe. They measure redshifts for millions of galaxies. Each measurement reveals that galaxies' distance and position in space. Redshift transformed astronomy from a two-dimensional sky map into a three-dimensional exploration of cosmic architecture. The most distant galaxies we can observe show the highest redshifts. Their light has been traveling for most of the universe's history. This ancient light carries information about cosmic birth. By measuring the redshift of the most distant observable objects, scientists can calculate when the universe began expanding. The math is straightforward, but the implications are staggering. Light with the highest redshift left its source when the universe was very young. Some galaxies show us conditions when the cosmos was only a few 100 million years old. The current record holder galaxies display redshifts indicating they formed when the universe was less than 5% of its current age. That's like seeing baby photos of cosmic history. These extreme redshift measurements revealed the universe is approximately about 13.8 billion years old. Modern astronomy has created the most ambitious project in scientific history. Astronomers are measuring redshifts for millions of galaxies to build a complete three-dimensional map of the observable universe. Each galaxy's redshift reveals its distance from Earth. Combined with its position in the sky, this creates a precise three-dimensional coordinate. Millions of these coordinates reveal cosmic structure on the largest scales. The results are breathtaking. Galaxies aren't scattered randomly through space. They form a cosmic web of filaments and voids. Massive galaxy clusters sit at intersections of cosmic highways. These redshift surveys revealed dark matter's invisible scaffolding. Matter flows along hidden pathways we can only detect through gravitational effects on visible galaxies. The universe's architecture emerges from the accumulated light of billions of distant worlds. Redshift gives scientists access to the universe's ultimate physics laboratory. Light from distant galaxies carries information about physical conditions billions of years ago. Scientists can test whether fundamental constants of nature have changed over cosmic time. The fine structure constant, electron mass, and other basic properties leave signatures in atomic spectra. So far, these tests confirm that physics worked the same way in the distant past. The laws of nature appear constant across cosmic history. This consistency allows scientists to trust their models of cosmic evolution. The same physics that operates in Earth laboratories governed the universe when it was young. Ancient light validates our understanding of how stars, galaxies, and cosmic structure formed over billions of years. Redshift observations provide the foundation for every major discovery in modern cosmology. Without redshift, we wouldn't know about cosmic expansion, the Big Bang, or dark energy. The discovery of accelerating expansion came from studying supernovae at different redshifts. Scientists found that distant supernovae appeared dimmer than expected. This revealed that cosmic expansion is speeding up. Dark energy, the mysterious force driving this acceleration, was discovered through redshift measurements. It comprises about 68% of the universe's total energy density. The Big Bang theory itself rests on redshift observations. Hubble's law extrapolated backward points to a moment when all cosmic distances were zero. Every major cosmic mystery we're trying to solve today began with the simple observation that distant starlight appears redder than it should. You hear this effect every day without thinking about it. An ambulance races toward you with its siren blaring. The pitch sounds high and urgent. Then it passes by and speeds away. The siren's pitch drops dramatically. Same siren, same volume setting, completely different sound. This isn't your imagination playing tricks. It's one of the most fundamental principles in physics. Scientists call this the Doppler effect, the change in wave frequency when the source moves relative to the observer. Your ears detect this change because sound waves get compressed or stretched during motion. When the ambulance approaches, it catches up to its own sound waves. This squashes the waves together. Higher frequency means higher pitch. When it moves away, the ambulance leaves its sound waves behind. The waves stretch apart. Lower frequency creates the deeper tone you hear after it passes. This everyday experience reveals a universal law that governs everything from police radar to cosmic redshift. Imagine dropping stones into a calm pond. Each stone creates circular ripples that spread outward at constant speed. Now picture walking across the pond while dropping stones. The ripples you create ahead of your path get bunched together. Behind you, they spread farther apart. Your motion changes the pattern even though each ripple travels at the same speed. Sound waves behave exactly like those water ripples. When a sound source moves toward you, it catches up to the waves it created moments earlier. This compresses the wavelengths. Shorter wavelengths mean higher frequency. When the source moves away, it abandons the waves it just made. The distance between wave peaks increases. Longer wavelengths create lower frequency. The waves themselves don't speed up or slow down. Only their spacing changes due to the source's motion. This compression and stretching principle applies to all types of waves: sound, light, radio, everything. The faster something moves, the more dramatic the frequency change becomes. This isn't a random effect. There's a precise mathematical relationship between speed and frequency shift. Think of a race car accelerating past the grandstand. At low speeds, the pitch change is subtle. As the car reaches higher velocities, the Doppler shift becomes much more noticeable. The key factor is relative velocity, how fast the source and observer approach or separate from each other. If both are moving, only their relative motion matters. Scientists use this speed-dependent relationship to measure velocities. Police radar works this way. The frequency change in reflected radio waves reveals exactly how fast vehicles are traveling. The same principle lets astronomers measure how fast stars rotate or how quickly binary star systems orbit each other. Light behaves as a wave just like sound. When light sources move, they create the same compression and stretching effects. But instead of hearing pitch changes, we see color changes. Blue light has short wavelengths. Red light has longer wavelengths. When a light source approaches you, its waves get compressed toward shorter wavelengths. This shifts the light toward the blue end of the spectrum. When the source moves away, the light waves stretch toward longer wavelengths. The light appears redder than it would if the source were stationary. This color shifting happens with any electromagnetic radiation. Visible light radio waves, X-rays, gamma rays, all follow the same Doppler principle. Astronomers use this effect constantly. They can tell whether stars are moving toward or away from Earth just by analyzing the colors in starlight. Scientists have specific names for these color changes. When light shifts toward shorter wavelengths, they call it blue shift. When it shifts toward longer wavelengths, they call it redshift. A blue shift means the light source is approaching. Think of it as light getting squeezed toward the blue end of the spectrum. Police car headlights would appear slightly bluer as the car races toward you. Redshift means the source is receding. The light gets stretched toward the red end. Those same headlights would look slightly redder as the car speeds away. The amount of shift reveals the speed of approach or recession. Tiny shifts indicate slow motion. Larger shifts mean faster velocities. This color-coding system became astronomy's primary tool for measuring cosmic motions across the universe. The wavelength change follows a simple mathematical relationship. Scientists compare the observed wavelength to the expected wavelength from a stationary source. The difference reveals the relative velocity directly. If a hydrogen line normally appears at 656 nanometers, but you observe it at 660 nanometers, you can calculate exactly how fast the source is moving away. This formula works for any type of wave at any frequency. Radio astronomers use it with radio waves. Optical astronomers apply it to visible light. X-ray astronomers employ it with high-energy radiation. The precision is remarkable. Astronomers can detect velocity changes as small as walking speed in stars thousands of light-years away. This measurement technique revolutionized our understanding of stellar motions and galactic structure. For objects moving much slower than light speed, the Doppler calculation becomes remarkably simple. The frequency change equals the source velocity divided by the wave speed. This approximation works perfectly for cars, trains, aircraft, and most terrestrial applications. Even supersonic jets move slowly compared to light speed. Police radar uses this simplified version. The frequency shift in reflected microwaves directly indicates vehicle speed. No complex relativistic corrections needed. The same formula applies to sound waves from moving sources. Meteorologists use Doppler radar to track storm systems and measure wind speeds inside hurricanes. Most astronomical applications also use this classical approximation since stellar motions rarely approach light speed. Strange things happen when objects approach the speed of light. The simple Doppler formula breaks down completely. Einstein's relativity takes over. At extreme velocities, time itself dilates relative to the observer. This adds an extra factor to the frequency shift beyond simple wave compression. The effect becomes much more dramatic than classical physics predicts. Particles in accelerators experience this relativistic Doppler effect. Their radiation appears vastly shifted compared to stationary sources. Some astronomical objects reach these extreme speeds. Quasar jets and particles near black holes require relativistic Doppler calculations. These high-speed effects provided early confirmation of Einstein's special relativity theory. Every police radar gun demonstrates the Doppler effect in action. The device sends out radio waves at a specific frequency. These waves bounce off moving vehicles and return to the gun. The reflected waves carry a frequency shift that reveals the vehicle's speed. Approaching cars compress the radio waves. Receding cars stretch them out. The radar computer calculates speed from the frequency difference between transmitted and received signals. The entire process takes fractions of a second. This same technique works with sound waves. Some speed detection systems use ultrasonic Doppler rather than radio waves. The principle extends to weather radar, which tracks precipitation motion and wind patterns using Doppler-shifted radio reflections. Doppler measurements unlock stellar mysteries invisible through direct observation. Stars rotate on their axes like planets. This rotation creates predictable Doppler patterns in stellar light. One edge of the star moves toward Earth while the opposite edge recedes. This splits spectral lines into characteristic shapes that reveal rotation speeds. Binary star systems orbit around their common center of mass. As they circle each other, their Doppler shifts change periodically. These variations reveal orbital periods, masses, and system geometry. Even planets orbiting distant stars create tiny Doppler wobbles in their host star's light. These minuscule shifts led to the discovery of thousands of exoplanets. The Doppler effect transformed astronomy from studying static stellar positions to measuring the dynamic motions that govern cosmic structure. Distance and speed follow a perfect mathematical relationship throughout the observable universe. Edwin Hubble discovered this pattern by measuring galaxies at different distances from Earth. Every galaxy beyond our local neighborhood follows the same rule. Double the distance, and the recession speed doubles as well. Triple the distance, and the speed triples. This isn't coincidence or measurement error. It's a fundamental law governing cosmic structure. Scientists call it Hubble's law, the linear relationship between galactic distance and recession velocity. The pattern reveals something extraordinary about space itself. Galaxies aren't flying through the universe randomly. They're being carried apart by the expansion of space. Hubble's law provided the first direct evidence that our universe is growing larger with time. Picture drawing dots on a deflated balloon with a marker. Now slowly inflate the balloon while watching the dots. They move apart from each other, but the dots themselves aren't traveling across the balloon's surface. The balloon material stretches between them. The dots remain stationary relative to their local patch of rubber. Yet from any dot's perspective, all the others appear to recede. Space behaves exactly like that balloon. Galaxies sit essentially motionless within their local regions of spacetime, but the cosmic fabric itself expands uniformly in all directions. This explains why every distant galaxy appears to flee from the Milky Way. We're not special. From any galaxy's perspective, all others seem to race away. Space expansion is fundamentally different from objects moving through space. Scientists need a way to describe how much the universe has grown since any particular moment in cosmic history. They use something called the scale factor, a number that represents the universe's relative size. Think of it like a zoom setting on a camera. If today's universe has a scale factor of 1, then a universe half the size would have a scale factor of 0.5. When the universe was very young, space was much more compressed. The scale factor was tiny. As billions of years passed, space expanded and the scale factor increased. This number lets astronomers calculate exactly how much space has grown during light's journey from distant galaxies. The scale factor provides a precise way to track cosmic expansion throughout the universe's entire history. Light waves get carried along as space expands beneath them. This creates a unique type of wavelength stretching that differs completely from the Doppler effect. Imagine an ant walking across a stretching rubber sheet. As the sheet expands, the distance between the ant's footsteps increases. The ant maintains constant speed, but its trail gets longer. Light behaves similarly in expanding space. Photons maintain constant speed, but the space they travel through grows larger during their journey. This stretches their wavelengths proportionally. The amount of stretching reveals how much space expanded while the light was traveling. More expansion means longer wavelengths and greater redshift. This wavelength stretching preserves a record of cosmic expansion in every photon that reaches Earth. Cosmological redshift operates by completely different physics than ordinary Doppler shifts. The Doppler effect requires relative motion through space. Cosmological redshift requires no motion at all. Local Doppler shifts happen when galaxies move toward or away from each other through their surrounding space. These motions are limited by the speed of light and create modest frequency changes. Cosmological redshift has no speed limit. Space itself can expand faster than light without violating relativity. This creates redshift values far larger than any Doppler effect could produce. The two effects can combine in astronomical observations, but only cosmological redshift explains the systematic recession of distant galaxies. Understanding this distinction revolutionized astronomy's interpretation of cosmic observations. Albert Einstein's general relativity provides the mathematical framework for understanding cosmic expansion. Russian mathematician Alexander Friedmann derived specific equations from Einstein's theory. These equations describe how the universe's expansion rate changes over time. They include factors for matter density, energy density, and cosmic curvature. The mathematics reveals that expansion rate depends on the total contents of space. More matter slows expansion through gravitational attraction. Dark energy accelerates it. Solutions to these equations predict how redshift should vary with distance under different cosmic conditions. Observations can test which solution matches reality. Friedmann's equations became the foundation of modern cosmology and Big Bang theory. In the 1990s, astronomers studied exploding stars called Type 1a supernovae at various distances. These stellar explosions all reach similar peak brightness. making them excellent cosmic distance markers. Something unexpected appeared in the data. The most distant supernova looked dimmer than predicted. This meant they were farther away than calculations suggested. The universe was expanding faster when those supernovae exploded than astronomers had assumed. Cosmic expansion was actually accelerating, not slowing down. This discovery revealed dark energy, a mysterious component that comprises about 68% of the universe's total energy. Dark energy drives accelerating expansion. The 2011 Nobel Prize in Physics honored this revolutionary discovery made possible by redshift measurements. Astronomers needed a standardized way to express redshift measurements. They created a parameter called z that represents the fractional change in wavelength. The formula is simple. Take the observed wavelength, subtract the original wavelength, then divide by the original wavelength. This gives you z. A redshift of z equals 0.1 means the wavelength increased by 10%. A redshift of z equals 1 means it doubled. Higher z values indicate more extreme wavelength stretching. This parameter lets scientists communicate redshift measurements precisely. It works for any type of electromagnetic radiation at any frequency. The z parameter became astronomy's universal language for describing cosmic distances and cosmic time. The highest redshift objects visible through telescope show us the universe when it was young and dramatically different. These ancient galaxies display redshift values exceeding z equals 10. Light from these distant sources began its journey when the universe was less than 500 million years old. That's only about 4% of the cosmos's current age. These early galaxies appear smaller, more irregular, and more actively star-forming than modern spiral galaxies. They reveal cosmic conditions during the universe's adolescent phase. High redshift observations show how cosmic structure evolved over billions of years. They provide direct evidence for theories about galactic formation and growth. Each new redshift record pushes our view closer to the Big Bang itself. Simple proportional relationships break down at very large redshift values. The universe's expansion rate has changed dramatically over cosmic history. Early in cosmic history, matter dominated the universe's energy budget. This caused expansion to decelerate. Later, dark energy took control and began accelerating expansion. These changing conditions create nonlinear relationships between redshift and distance for extremely distant objects. The simple Hubble law becomes inadequate. Advanced cosmological models account for these complications. They include the changing balance between matter, radiation, and dark energy throughout cosmic evolution. Understanding these nonlinear effects is crucial for interpreting observations of the most distant galaxies. Large-scale galaxy surveys measure redshifts for millions of cosmic objects. This data reveals the three-dimensional distribution of matter throughout observable space. The pattern of galaxy clustering depends on the universe's geometry and composition. Different amounts of dark matter and dark energy produce different clustering signatures. By comparing observed redshift distributions with theoretical predictions, astronomers can determine cosmic parameters precisely. This includes the universe's age, composition, and ultimate fate. These surveys confirm that our universe is geometrically flat and dominated by dark energy. They provided independent verification of the accelerating expansion discovery. Redshift mapping became cosmology's primary tool for testing fundamental theories about cosmic structure. If dark energy continues driving accelerating expansion, the universe faces a dramatic long-term future. cosmic acceleration will eventually separate all galaxy clusters beyond observable limits. In hundreds of billions of years, galaxies outside our local group will become invisible due to extreme redshift. Their light will be stretched beyond any possible detection. The ultimate scenario is called the Big Rip. Space expansion would accelerate without limit, eventually tearing apart galaxies, stars, planets, and atoms themselves. Redshift measurements of distant supernova provide the primary evidence for this accelerating expansion. Future observations will test whether acceleration continues indefinitely. The same redshift that revealed cosmic expansion may be chronicling the universe's approach to its final destiny. Einstein's general relativity made a startling prediction about light in strong gravitational fields. Photons climbing out of intense gravity should lose energy during their escape. This energy loss appears as a wavelength shift toward the red end of the spectrum. The stronger the gravity, the more dramatic the redshift becomes. The effect has nothing to do with motion. Gravity itself warps spacetime in ways that affect electromagnetic radiation. Light frequencies change simply by traveling through curved space. Einstein calculated this phenomenon decades before anyone could measure it. His mathematics predicted that massive objects would stretch light wavelengths just by existing. Gravitational redshift became one of the key tests that confirmed general relativity's revolutionary description of gravity. Imagine riding in an elevator with no windows. The elevator accelerates upward at exactly 9.8 meters per second squared. You feel pressed against the floor with normal Earth-like weight. Einstein realized you cannot tell whether you're accelerating through space or sitting stationary in Earth's gravity field. These two situations are physically equivalent. This equivalence principle reveals something profound about time. Acceleration creates time dilation effects. Since gravity is equivalent to acceleration, gravity must also dilate time. Clocks in stronger gravitational fields run slower relative to clocks in weaker fields. This time difference affects the frequency of light emitted from those regions. The equivalence principle showed that gravity doesn't just bend space, it bends time itself. Time flows at different rates depending on gravitational field strength. This isn't philosophy or theory. It's a measurable physical effect with practical consequences. A clock sitting on Earth's surface runs slightly slower than an identical clock in orbit. The difference is tiny but precisely calculable. Stronger gravity means slower time. This time dilation directly affects light frequencies. Atoms in strong gravity fields oscillate more slowly from an outside observer's perspective. Their light appears redshifted. The effect scales with field strength. Neutron stars create dramatic time dilation. Black holes produce extreme effects. Even Earth's gentle gravity creates measurable shifts. Gravitational time dilation links space-time and electromagnetic radiation in Einstein's unified framework. Gravitational redshift strength depends directly on escape velocity from the light source's location. This connection reveals the deep relationship between gravity and electromagnetic radiation. Escape velocity measures how fast you'd need to travel to completely escape a gravitational field. Earth's escape velocity is about 11 kilometers per second. The Sun's is over 600 kilometers per second. Higher escape velocities mean stronger gravitational fields. Stronger fields create larger redshift effects. The relationship follows precise mathematical rules. White dwarf stars have escape velocities around 5,000 kilometers per second. Neutron stars reach 150,000 kilometers per second. Each produces proportionally larger gravitational redshift. This velocity connection allows astronomers to measure gravitational field strengths using only light frequency measurements. White dwarf stars provided the first clear astronomical test of gravitational redshift. These stellar remnants pack the Sun's mass into Earth-sized volumes. Their extreme density creates gravitational fields thousands of times stronger than Earth's. Light escaping from their surfaces must climb out of these intense gravity wells. Astronomers measured the spectrum of white dwarf starlight in the early 1900s. Every spectral line appeared shifted toward longer wavelengths compared to normal stars. The amount of shift matched Einstein's predictions exactly. This confirmed that gravity really does affect light frequencies independent of any motion effects. White dwarf observations provided crucial early evidence supporting general relativity's description of space-time curvature. Your smartphone's GPS wouldn't work without accounting for gravitational time dilation. Satellites orbit about 20,000 kilometers above Earth's surface where gravity is weaker. Clocks on GPS satellites run faster than identical clocks on the ground. The difference amounts to about 38 microseconds per day. That sounds tiny, but GPS requires nanosecond precision. Without gravitational corrections, GPS positions would drift by several kilometers per day. Navigation systems would become useless within hours. Engineers program the satellites to compensate for this time difference. They adjust clock rates to account for both gravitational effects and orbital motion. GPS represents gravitational redshift's most widespread practical application in modern technology. At a black hole's event horizon, gravitational redshift approaches infinity. This boundary represents the point where escape velocity equals light speed. Light emitted just outside the horizon appears extremely redshifted to distant observers. As the emission point gets closer to the horizon, the redshift increases without limit. At the exact horizon location, photons require infinite time to climb out of the gravitational well. From an outside perspective, light appears to freeze and fade away. This infinite redshift effect makes the event horizon truly black. No electromagnetic radiation can escape to reach external detectors. The event horizon represents the ultimate demonstration of gravity's power over light and time. In 1960, physicists Robert Pound and Glenn Repka performed the most precise test of gravitational redshift ever attempted. They used a 22.5-meter tower at Harvard University. Gamma rays emitted at the bottom of the tower climbed against Earth's gravity to detectors at the top. The height difference created a tiny but measurable gravitational redshift. The frequency shift was incredibly small, only about 2 parts in 1,000 trillion, but their experimental technique was sensitive enough to detect this minuscule effect. Their measurement agreed with Einstein's prediction to within experimental uncertainty. This laboratory confirmation proved gravitational redshift works even in Earth's weak gravity field. The Pound-Repka experiment demonstrated that general relativity applies to all scales from laboratory towers to cosmic black holes. Neutron stars create some of the strongest gravitational fields in the known universe. These stellar remnants pack more mass than our Sun into spheres only 20 kilometers across. Surface gravity on neutron stars exceeds Earth's by factors of 100 billion. Light escaping from these surfaces experiences enormous gravitational redshift effects. Astronomers observe neutron star spectra to measure these extreme redshift values. The measurements reveal surface gravitational field strengths and stellar mass estimates. Some neutron stars approach the theoretical maximum mass limit before collapsing into black holes. Their gravitational redshift measurements probe the limits of matter itself. Neutron star observations provide natural laboratories for testing gravity under the most extreme conditions possible. Even our Sun shows measurable gravitational redshift variations across its surface. The effect is strongest at the solar limb, the edge of the Sun's visible disk. Light from the solar limb travels slightly farther through the Sun's gravitational field compared to light from the center. This creates a small additional redshift. The difference is tiny, only about 600 meters per second in equivalent velocity units. But modern spectrographs can detect this subtle variation. Solar limb measurements helped confirm that gravitational redshift depends on the detailed path light takes through curved space-time. These observations showed that gravity affects light propagation in complex ways beyond simple surface effects. When radio signals pass close to massive objects, they experience both time delays and frequency shifts. Physicist Erwin Shapiro first calculated this effect in the 1960s. Radio waves traveling past the Sun take longer to reach their destination than they would in empty space. The time delay results from light following curved spacetime geometry. The delayed arrival also comes with a frequency shift. Radio waves climbing out of the Sun's gravity will emerge at slightly lower frequencies. Spacecraft communications provide perfect opportunities to measure Shapiro delay effects. Signals passing behind the Sun show precisely the delays Einstein's theory predicts. These measurements confirm that massive objects curve spacetime in ways that affect both signal timing and electromagnetic frequency. What if you could read light like a book? Spectroscopy makes this possible by separating light into its individual wavelength components. Think of white light passing through a prism. The prism spreads the light into a rainbow of colors. Each color represents a different wavelength of electromagnetic radiation. Spectroscopy works the same way but with much greater precision. Scientists use special instruments to split starlight into thousands of narrow wavelength bands. Each band reveals specific information about the light source. The resulting spectrum looks like a barcode. Bright regions show wavelengths where the source emits strongly. Dark lines appear where certain wavelengths get absorbed. This wavelength analysis became astronomy's primary tool for measuring redshift and understanding cosmic objects. Every chemical element creates a unique pattern in light spectra. Hydrogen produces specific absorption lines at predictable wavelengths. Helium creates different lines. Iron has its own distinctive signature. These spectral lines work like fingerprints. No two elements produce identical patterns. Astronomers can identify which elements exist in distant stars just by analyzing their light. Each element absorbs light at precisely defined wavelengths determined by atomic physics. These wavelengths never change under normal conditions. They provide absolutely reliable reference points. When astronomers observe these same lines shifted to different wavelengths in galactic spectra, they know redshift has occurred. The amount of shift reveals exactly how much the light has been stretched. Elemental fingerprinting transformed astronomy from studying brightness to analyzing composition and motion. Measuring redshift requires comparing astronomical observations with laboratory reference standards. Scientists must know the exact rest wavelengths before they can detect any shifts. Laboratory spectroscopy provides these reference measurements. Physicists use precisely controlled conditions to measure where each elemental line should appear in the spectrum. The hydrogen alpha line, for example, has a rest wavelength of 656.3 nanometers. When this line appears at 659.8 nanometers in a galactic spectrum, astronomers can calculate the redshift precisely. The difference between observed and rest wavelengths directly reveals the redshift value. Larger differences mean higher redshift and greater distance. This comparison method gives astronomers absolute confidence in their redshift measurements. Modern astronomy cannot function without charge-coupled devices. These are electronic sensors that detect and record light digitally. CCDs revolutionized spectroscopic measurements in the 1980s. Before CCDs, astronomers used photographic plates that recorded only about 2% of incoming light. CCDs capture over 90% of the photons that hit them. This dramatic improvement made faint object spectroscopy possible. CCDs also record spectra simultaneously across wide wavelength ranges. A single exposure can cover the entire visible spectrum from blue to red. This allows comprehensive redshift analysis in minutes. The digital format eliminates measurement uncertainties from film development and grain structure. Computer processing extracts precise wavelength measurements from CCD data. CCD technology enabled the large-scale redshift surveys that mapped cosmic structure throughout the observable universe. Some redshift measurements require extraordinary precision. HL spectrographs provide the highest wavelength resolution possible with current technology. These instruments use a special grating that spreads light across many different orders simultaneously. Think of it like creating multiple overlapping spectra at different scales. The result is spectral resolution fine enough to detect velocity changes as small as 1 meter per second. This precision reveals tiny Doppler shifts from orbiting planets around distant stars. HL spectrographs can measure wavelengths to better than 1 part in 100,000. This accuracy makes possible the most demanding astronomical applications. Ultra-high-resolution spectroscopy opened new frontiers in exoplanet detection and stellar physics research. How do you get starlight from a massive telescope to a sensitive spectrograph without losing precious photons? Fiber optic cables provide the elegant solution. Traditional systems required mounting spectrographs directly on telescopes. This created vibration problems and limited spectrograph design options. Heavy instruments affected telescope pointing accuracy. Optical fibers carry light efficiently over long distances without significant loss. Spectrographs can now be installed in stable, temperature-controlled rooms while telescopes track objects smoothly. Each fiber acts like a tiny light pipe. Multiple fibers can feed light from different telescope positions to a single spectrograph simultaneously. Fiber optic systems enabled the construction of massive multi-object spectrographs for large-scale redshift surveys. Traditional spectroscopy could only study one object at a time. This limitation made large-scale surveys impossibly time-consuming until multi-object systems changed everything. Modern instruments can observe hundreds of galaxies simultaneously during a single telescope exposure. Special masks or fiber positioning systems direct light from many objects into one spectrograph. Each object gets its own dedicated section of the detector. Computer software separates and analyzes individual spectra from the combined data. This multiplies observational efficiency by factors of hundreds. Large redshift surveys like the Sloan Digital Sky Survey measured over 1 million galaxy redshifts using multi-object techniques. This capability transformed redshift measurement from individual object studies to comprehensive cosmic mapping projects. the most distant galaxies present a fundamental observational challenge. Their extreme redshift pushes visible light into infrared wavelengths beyond human vision. Light that started as ultraviolet or blue from young, hot stars gets stretched into infrared radiation by the time it reaches Earth. Optical telescopes cannot detect this shifted light. Infrared spectrographs use special detectors sensitive to longer wavelengths. These instruments can observe galaxies with redshifts exceeding Z=6, light from when the universe was less than 1 billion years old. Space-based infrared telescopes avoid Earth's atmospheric interference. The James Webb Space Telescope specialized in infrared observations of high redshift objects. Infrared spectroscopy extended redshift measurements to the most distant observable galaxies in cosmic history. Modern redshift surveys generate overwhelming amounts of data. Measuring millions of galaxy redshifts by hand would take centuries of human effort. Computer algorithms now perform most redshift measurements automatically. Software identifies spectral lines, measures their wavelengths, and calculates redshift values without human intervention. These automated pipelines process thousands of spectra per hour. Machine learning techniques recognize patterns in noisy data that might challenge human analysts. Quality control systems flag uncertain measurements for manual review. The combination of automation and human oversight ensures reliable results from massive datasets. Automated processing made possible the largest three-dimensional maps of cosmic structure ever created. Precise redshift measurement demands careful attention to systematic errors. Multiple factors can introduce false wavelength shifts that mimic genuine cosmological redshift. Earth's atmosphere absorbs certain wavelengths and creates its own spectral lines. Calibration exposures of comparison lamps remove these atmospheric effects from astronomical spectra. Instrument flexure and temperature changes can shift wavelength scales slightly. Regular calibration measurements track these variations and correct for them in data processing. Systematic errors of just a few parts per million can significantly affect redshift accuracy. Modern calibration systems achieve wavelength precision better than 10 meters per second. These meticulous calibration procedures ensure that redshift measurements reflect genuine cosmic expansion rather than instrumental artifacts. Measuring cosmic distances requires a careful chain of calibrations, starting with nearby objects. Astronomers cannot directly measure the distance to remote galaxies. They must build a distance ladder step by step. The process begins with objects close enough to measure through direct methods. Stellar parallax works for nearby stars. Radar ranging measures distances within the solar system. Each rung of the ladder depends on the previous one. Nearby measurements calibrate middle distance techniques. Middle distance methods calibrate far distance approaches. Any error in early steps gets magnified throughout the entire chain. This makes the lowest rungs critically important for cosmic distance measurements. The distance ladder connects human scale measurements to the largest structures in the observable universe. How fast is the universe expanding right now? The Hubble constant quantifies the current cosmic expansion rate by relating galaxy distances to their recession velocities. Scientists measure distances to nearby galaxies using multiple independent techniques. They also measure those same galaxies' redshift velocities from spectroscopic observations. The ratio of velocity to distance gives the Hubble constant. It is typically expressed as kilometers per second per megaparsec. Current measurements yield values around 70 kilometers per second per megaparsec. This number reveals how much the universe has grown since the Big Bang. It also predicts the ultimate fate of cosmic expansion. Precise Hubble constant measurement requires extraordinarily accurate distance determinations to nearby calibrator galaxies. Certain astronomical objects have predictable intrinsic brightness regardless of their location. These standard candles allow astronomers to calculate distances through brightness comparisons. Think of comparing streetlights at night. If you know a bulb's actual wattage, you can estimate its distance by measuring how bright it appears to you. Astronomical standard candles work the same way. Scientists identify objects with known absolute brightness, then measure their apparent brightness from Earth. The difference between intrinsic and observed brightness reveals the distance. Fainter objects must be farther away if they have identical intrinsic luminosity. Standard candle techniques provide distance measurements independent of any cosmic expansion effects or redshift relationships. When white dwarf stars exceed a critical mass limit, they explode as type I supernovae. These stellar detonations reach remarkably consistent peak brightness. The explosion physics ensures that all type I supernovae achieve similar maximum luminosity. This makes them excellent standard candles for cosmic distance measurement. Type I supernovae are bright enough to see in galaxies billions of light years away. They provide the only reliable distance measurements for extremely remote objects. In the 1990s, supernova observations revealed that cosmic expansion is accelerating. This discovery led to the identification of dark energy. Type I supernovae remain the gold standard for measuring cosmic distances beyond the reach of other techniques. A special class of pulsating stars provides precise distance measurements to nearby galaxies. Cepheid variables change brightness in regular cycles that reveal their intrinsic luminosity. These stars follow a period luminosity relationship discovered by Henrietta Leavitt. Longer pulsation periods correspond to higher intrinsic brightness. Astronomers measure a Cepheid's pulsation period, which tells them its absolute brightness. Comparing this to its observed brightness gives the distance. The Hubble Space Telescope revolutionized Cepheid distance measurement by observing these stars in galaxies up to 100 million light-years away. Cepheid distances provide the crucial calibration for more distant standard candle measurements like Type I supernova. Galaxy surface brightness varies randomly due to statistical fluctuations in stellar populations. These brightness variations provide an independent distance measurement method. More distant galaxies show smoother surface brightness because individual bright stars become unresolvable. Statistical fluctuations decrease with distance in predictable ways. This technique works particularly well for elliptical galaxies with uniform stellar populations. The fluctuation analysis requires high-quality imaging data. Surface brightness fluctuation measurements provide valuable cross-checks for other distance determination methods. Multiple techniques reduce systematic uncertainties. Independent distance methods ensure reliability when measuring the cosmic distance scale and calibrating the Hubble constant. Simple proportional relationships between redshift and distance break down at very large scales. The universe's geometry and expansion history create curvature in this relationship. Hubble's law assumes constant expansion rate throughout cosmic history. In reality, expansion rate has changed dramatically over billions of years. Early in cosmic history, matter dominated the universe and slowed expansion through gravity. Later, dark energy took control and began accelerating expansion. These changing conditions create nonlinear relationships between redshift and distance for extremely distant objects. Simple linear extrapolation becomes inadequate. Understanding curvature effects requires detailed cosmological models that account for the universe's complete expansion history. Large-scale galaxy surveys reveal how matter clusters throughout cosmic space and time. This clustering pattern depends sensitively on the universe's fundamental properties. Scientists compare observed galaxy clustering with theoretical predictions for different cosmological models. The best match reveals cosmic composition and geometry. Current observations indicate the universe is geometrically flat and dominated by dark energy. Dark matter comprises about 27% of cosmic energy density. These parameter measurements provide independent confirmation of results from cosmic microwave background observations and supernova studies. Precise cosmological parameter determination requires millions of galaxy redshift measurements across representative cosmic volumes. Sound waves in the early universe left fossilized imprints in today's galaxy distribution. These baryon acoustic oscillations provide a standard ruler for measuring cosmic distances. Before cosmic microwave background formation, sound waves propagated through hot plasma at the speed of sound. These waves had a characteristic wavelength of about 500 million light-years. When the universe cooled and became transparent, the sound waves froze in place. They appear today as preferred galaxy separation distances. This acoustic scale provides a distance standard because the sound horizon size is precisely calculable from early universe physics. Baryon acoustic oscillation measurements offer independent distance calibration that doesn't rely on the traditional distance ladder. Multiple distance measurement techniques must agree before astronomers accept cosmic distance determinations. Independent methods provide crucial systematic error checks. Cepheid variables, surface brightness fluctuations, and gravitational lensing time delays all measure distances to the same nearby galaxies. Agreement validates individual techniques. For remote objects, Type I supernovae, baryon acoustic oscillations, and cosmic microwave background observations provide independent distance scales. Consistency builds confidence. Disagreements between methods reveal systematic errors or incomplete understanding. Resolving discrepancies often leads to improved measurement techniques. The convergence of independent distance measurements strengthens our confidence in cosmic distance determinations and fundamental cosmological parameters. Modern cosmology faces troubling disagreements between different approaches to measuring cosmic distances and expansion rates. The Hubble tension represents the most significant conflict. Local distance measurements using cepheids and supernova give one value for the Hubble constant. Cosmic microwave background observations provide a different result. The discrepancy exceeds measurement uncertainties. Next-generation telescopes aim to resolve this tension through improved distance measurements. The James Webb Space Telescope provides unprecedented infrared sensitivity for cepheid observations. Large ground-based surveys will measure millions of additional galaxy distances. Statistical power from massive datasets should identify systematic errors. Resolving the Hubble tension may require discovering new physics or identifying subtle measurement biases in current techniques. Light from distant galaxies carries a timestamp from the past. The farther away a galaxy sits, the longer its light took to reach Earth. This travel time is called lookback time. When you observe a galaxy 1 billion light-years away, you see it as it existed 1 billion years ago. The light left that galaxy when Earth was much younger. Dinosaurs roamed our planet when that ancient starlight began its journey. This isn't theory or speculation. It's the fundamental nature of light propagation. Light travels at finite speed, so distance automatically equals time delay. Astronomers use redshift to calculate exactly how far back in time they're looking. Higher redshift means older light and earlier cosmic epochs. Every telescope observation becomes a time machine, showing us the universe's history preserved in ancient starlight. Why do galaxies at different distances look so dramatically different from each other? The answer lies in cosmic evolution. The universe has changed fundamentally over billions of years. Nearby galaxies appear mature and well-organized. They display beautiful spiral arms or smooth elliptical shapes. Their star formation rates are relatively modest. Distant galaxies look chaotic and irregular. They show violent star formation activity in bizarre structures. Many appear to be in the process of merging with neighbors. This difference reflects genuine evolution. Early galaxies really were smaller, more active, and less organized than modern ones. Redshift observations provide direct evidence for how cosmic structure developed from primordial chaos to today's organized galaxy families. The universe experienced a dramatic period of stellar birth during its adolescent phase. Astronomers call this era cosmic noon, when star formation rates peak throughout space. Galaxies at moderate redshift values show star formation rates 10 times higher than typical modern galaxies. Young, hot stars dominated these ancient stellar populations. The universe was manufacturing stars at a frantic pace during this epoch. Gas supplies were abundant and relatively undisturbed by previous stellar generations. Over cosmic time, star formation gradually declined. Gas supplies became depleted. Heavy elements polluted pristine hydrogen clouds. The universe's stellar birth rate slowed dramatically. Today's universe produces new stars at only a fraction of the rate during cosmic noon. Ancient galaxies were fundamentally different creatures than the massive spiral and elliptical systems we see today. Early galaxy formation involved constant mergers and violent interactions. High redshift observations reveal small, irregular galaxy fragments in the process of assembling. These building blocks were much smaller than modern galaxies. Gravitational interactions were more frequent in the dense early universe. Galaxy collisions triggered intense star formation bursts and reshaped galactic structures. The smooth, organized galaxies we observe nearby formed through billions of years of mergers and quieter evolution. Today's cosmic architecture emerged from primordial chaos. Redshift surveys trace this assembly process across cosmic time by observing galaxies at different evolutionary stages. Stars forge heavy elements in their nuclear furnaces and distribute them through space when they die. This process gradually enriches the universe with metals, astronomers' term for all elements heavier than hydrogen and helium. The earliest galaxies contained almost pure hydrogen and helium left over from the Big Bang. These pristine compositions show up in high redshift galaxy spectra. As stellar generations lived and died, they contaminated surrounding gas with newly forged elements. Iron, oxygen, carbon, and silicon accumulated over cosmic time. Modern galaxies display much higher metal abundances than their ancient counterparts. The difference reveals billions of years of stellar chemical processing. Redshift measurements trace this chemical enrichment across cosmic history by comparing elemental abundances at different epochs. During the universe's middle age, supermassive black holes grew rapidly and powered some of the most luminous objects ever observed. These active galactic nuclei are called quasars. Quasi-stellar radio sources. Quasars at high redshift vastly outshine their host galaxies. They appear as brilliant beacons visible across cosmic distances. Their luminosity comes from matter falling into central black holes. The quasar population peaked when the universe was roughly 1/4 its current age. This epoch represents the most active phase of black hole growth in cosmic history. Modern galaxies contain similar supermassive black holes, but most are now dormant. They exhausted their surrounding gas supplies and shut down their intense radiation. The decline of quasar activity reveals how galactic evolution depleted central gas reservoirs over billions of years. The universe experienced a fundamental phase transition during its first billion years. Primordial hydrogen gas changed from neutral atoms to ionized plasma in a process called cosmic reionization. The first stars and galaxies generated intense ultraviolet radiation that stripped electrons from hydrogen atoms throughout space. This radiation gradually ionized the entire universe. High redshift observations reveal this reionization process in action. Distant quasar spectra show characteristic absorption signatures from intervening neutral hydrogen. The timing of reionization indicates when the first stellar populations became powerful enough to affect cosmic-scale gas properties. This epoch marked the end of the cosmic dark age, the beginning of the universe's current radiation-filled state. Roughly 10 billion years ago, the universe reached its most productive phase of stellar manufacturing. Star formation rates during cosmic noon exceeded current levels by factors of 10 to 30. Galaxies at this epoch appear blue and chaotic in astronomical images. Massive star clusters illuminate surrounding gas clouds with intense ultraviolet radiation. The abundance of cold gas supplied fuel for this stellar baby boom. Galaxy mergers triggered additional star formation bursts through gravitational compression. Environmental conditions favored rapid stellar birth. Gas metallicity was low enough to allow efficient cooling and fragmentation into stellar nurseries. The cosmic noon epoch created most of the stellar mass we observe in today's universe. Large galaxies completed their major growth phases earlier than smaller systems. This counterintuitive pattern is called downsizing. Massive galaxies formed first despite requiring more material. The most massive elliptical galaxies show old stellar populations with little ongoing star formation. They assembled quickly during the early universe and then became quiescent. Smaller galaxies continue forming stars at significant rates even today. They represent late bloomers in the cosmic star formation story. This pattern reflects how different mass scales respond to cosmic expansion and structure formation. Massive systems can overcome expansion and collapse early. Downsizing reveals the complex relationship between galaxy mass, formation time, and evolutionary history. Between distant quasars and Earth lies a network of intergalactic S-clouds that create absorption lines in quasar spectra. This pattern is called the Lyman alpha forest. Each absorption line represents a gas cloud along the line of sight to the background quasar. The forest pattern reveals the distribution and properties of intergalactic medium. Higher redshift observations show denser forest patterns. The early universe contained more neutral hydrogen in filamentary structures. Over cosmic time, stellar radiation and galactic winds gradually ionized and dispersed this intergalactic gas. The forest becomes less dense at lower redshifts. This absorption line archaeology preserves the evolutionary history of gas between galaxies across billions of years. Do the fundamental laws of physics change over cosmic history? Redshift observations provide a unique laboratory for testing physical constant stability across billions of years. Atomic transitions depend precisely on fundamental constants like the fine structure constant and electron charge. Changes in these values would shift spectral line wavelengths. High redshift galaxy and quasar spectra show the same atomic line ratios as local laboratory measurements. Physical constants appear stable across cosmic time. This consistency validates using local physics to interpret ancient astronomical observations. The same natural laws operated when the universe was young. Constant verification gives astronomers confidence in their models of cosmic evolution and stellar nucleosynthesis. The James Webb Space Telescope revolutionized observations of the earliest galactic systems. Its infrared sensitivity can detect galaxies formed when the universe was less than 500 million years old. These primordial galaxies appear smaller and more irregular than expected. They show intense star formation despite their youth and small size. Some early galaxies contain surprisingly massive black holes for their age. This suggests rapid early growth processes that theoretical models struggle to explain. The first galaxies formed from tiny density fluctuations in the primordial universe. Dark matter provided gravitational scaffolding for normal matter accumulation. Webb's observations provide direct glimpses of galaxy formation during the universe's infancy, confirming and challenging theoretical predictions about cosmic dawn. Modern astronomy faces an unprecedented challenge. Scientists want to map the three-dimensional structure of the entire observable universe. This requires measuring redshift for millions of galaxies simultaneously. Projects like the Dark Energy Spectroscopic Instrument aim to measure 35 million galaxy redshifts over 5 years. That's nearly 20,000 measurements every single day. These surveys use robotic systems to position thousands of optical fibers automatically. Each fiber collects light from a different galaxy. A single exposure captures spectra from 5,000 objects at once. The resulting data creates the most detailed three-dimensional map of cosmic structure ever attempted. Scientists can trace how matter clusters and flows on the largest scales. Large-scale surveys represent astronomy's transition from studying individual objects to mapping the universe's complete architecture. What force drives the universe's accelerating expansion? Dark energy comprises about 68% of cosmic energy density, yet scientists don't understand what it is. Redshift measurements provide the primary tool for studying dark energy's properties. By mapping how expansion rate changes over cosmic time, astronomers can test different theoretical models. Type Ia supernovae at various redshifts reveal expansion history across billions of years. Their brightness-distance relationship shows whether dark energy's strength has remained constant. Current observations suggest dark energy behaves like Einstein's cosmological constant, a fixed energy density in empty space. But alternative theories predict time-varying behavior. Future redshift surveys will measure dark energy's properties with unprecedented precision and potentially reveal its true nature. Einstein's general relativity successfully explains gravity on solar system scales. But does it work correctly across cosmic distances and billions of years? Large-scale structure provides a laboratory for testing gravity on the grandest scales. Matter clustering depends sensitively on gravitational physics. Modified gravity theories predict different growth rates for cosmic structure compared to general relativity. These differences show up in galaxy clustering patterns. Redshift surveys measure how galaxy clustering changes with cosmic time. The growth rate of structure reveals whether Einstein's theory needs modification. Combining redshift data with gravitational lensing observations provides multiple independent tests of gravitational physics across cosmic history. Hydrogen is the universe's most abundant element. It creates a radio signal at 21 centimeters wavelength that penetrates cosmic dust and gas clouds. This neutral hydrogen emission traces cosmic structure during epochs invisible to optical telescopes. The signal reveals conditions during the universe's dark age and reionization. As the universe expands, this 21-centimeter radiation gets redshifted to longer wavelengths. Radio telescopes can observe these shifted signals from different cosmic epochs. Future radio arrays will map neutral hydrogen distribution across cosmic time. This provides a completely different view of structure formation and cosmic evolution. 21-centimeter cosmology opens observational windows to cosmic epochs that optical astronomy cannot access. When massive black holes merge, they create ripples in spacetime called gravitational waves. These signals carry redshift information just like electromagnetic radiation. Gravitational wave detectors measure the frequency evolution of merger signals. Cosmic expansion redshifts these frequencies during their journey to Earth. Combined electromagnetic and gravitational wave observations of the same events provide powerful cosmological constraints. The two types of signals probe space and time through different physics. This multi-messenger approach offers independent verification of cosmic expansion measurements. It reduces systematic uncertainties that affect individual observation types. Gravitational wave cosmology represents a revolutionary new tool for studying universe expansion and fundamental physics. When planets pass in front of their host stars, they create brief eclipses. Starlight filtering through planetary atmospheres reveals atmospheric composition. This transmitted light carries spectral signatures from atmospheric gases. Different molecules absorb light at characteristic wavelengths. As planets orbit their stars, atmospheric absorption lines show tiny Doppler shifts from orbital motion. These shifts reveal wind speeds and atmospheric dynamics. High-precision spectrographs can detect redshift changes smaller than human walking speed in exoplanet atmospheres. This precision opens new frontiers in planetary science. Atmospheric redshift measurements provide detailed information about weather, chemistry, and habitability on distant worlds. Modern surveys generate millions of galaxy spectra faster than human astronomers could possibly analyze. Artificial intelligence transforms this data deluge into scientific discoveries. Machine learning algorithms can recognize spectral patterns in noisy, complex data. Neural networks trained on millions of examples achieve superhuman accuracy in redshift measurement. These automated systems process spectra in real time as telescopes collect data. They identify interesting objects for detailed follow-up observations immediately. Artificial intelligence also discovers subtle patterns in large datasets that would escape human notice. Machine learning reveals correlations across millions of measurements. Automated redshift analysis enables scientific discoveries that would be impossible through traditional manual methods. Future ground-based and space telescopes will improve redshift measurement precision by factors of 10 to 100 over current capabilities. The extremely large telescope will collect light with a 39-meter primary mirror, larger than a basketball court. Its light-gathering power enables redshift measurements for the faintest distant galaxies. Space-based telescopes avoid atmospheric interference that limits ground-based precision. They can achieve wavelength stability better than 1 part in 10 billion. These improvements will measure cosmic expansion history with extraordinary detail. Scientists will detect tiny deviations from current cosmological models. Revolutionary telescope technology will answer fundamental questions about dark energy, inflation, and the universe's ultimate fate. The universe communicates through multiple channels: light, gravitational waves, cosmic rays, and neutrinos. Each messenger carries unique information about cosmic phenomena. Combining redshift measurements across different messenger types provides unprecedented insights into cosmic events. The same explosive events can be studied through complementary physics. Neutron star mergers produce both gravitational waves and electromagnetic signals. Comparing their redshift measurements tests fundamental assumptions about cosmic expansion. This multi-messenger approach reduces systematic errors that affect individual observation types. Independent measurements provide robust confirmation of cosmological results. Comprehensive multi-messenger observations represent the future of precision cosmology and astrophysics research. Contemporary cosmology faces troubling disagreements between different measurement methods. The Hubble tension refers to conflicting values of the universe's current expansion rate. Local measurements using nearby galaxies give one answer. Cosmic microwave background observations provide a different result. The discrepancy exceeds measurement uncertainties. Similar tensions appear in measurements of matter clustering strength and cosmic geometry. These conflicts suggest missing physics or systematic measurement errors. Future redshift surveys aim to resolve these tensions through independent, high-precision measurements. They will either confirm existing results or reveal new physics. Solving cosmology's tension problems may require revising fundamental assumptions about dark energy, dark matter, or cosmic evolution.